Should I backtrack? Here's your exam outline. Here's the no and no columns. Okay, examples. So it's to see if it's exact or homogeneous. What we need to do is we need to write it as a differential on each side. And so, and then the format of those equations have everything on one side set equal to 0, and then we identify your m and your n. So it doesn't matter which side you put it on, just for the sake of keeping the first one positive, we'll put it all on the right side. So our m is equal to this function, and our n is equal to -1. And if we check if it's exact, we'll see it's not. And then if we check if it's homogeneous, we have to replace the x's and y's with xt and yt. And if we do that, we can factor out a t here, but this has to be the same order, and it's not. It doesn't have anything, right? So it's not homogeneous either. So maybe this just isn't. There's probably some clever substitution that you can do to solve for this, but in terms of the list of things that was there, this is not linear, not exact, not homogeneous, not Bernoulli. So I don't think it's anything that we can do at our point. It's not separable. It depends on the instructions. So here, for the following, identify the order and whether or not it's linear. So I can say it's a first order nonlinear. Then for first order differential equations, identify which you would solve for this differential equation, the method. In this case, we don't seem to have a method that we learned to help us solve for this. So I think all we can say is that this is first order nonlinear. And that's about all we can say. And say can't solve using these methods. No, yeah, leave it. That would be another 20 minutes right there. Then you would identify the multiple methods that you could solve. Yeah, sure. There might be. I mean, there are differential equations that we've run into where we're learning how to do like homogeneous differential equations, but it happens to be exact. So there's two ways to solve it, and we're just in that particular section that's doing this way. But I think it's a good practice to be able to identify the different ways of solving for it in case you started working it out as an exact differential equation, then realized, oh, I'm stuck. Maybe I'll use a different method to solve for it. Okay. So what else? Circuits. Let's do a circuits problem. So fortunately, I have the book open. Right, where's the book? There's the book. And circuits are also nice differential equations because they're linear. So, I mean, ideally they'd be easier to solve, right? Well, not necessarily. So maybe let's try, I don't know, 29, 30, 32. So it's an RC RDQ All right, so we have a 200 volt electromotive force in an RC series circuit in which the resistance is 1,000 ohms and capacitance is this thing. Find the charge Q. So you're looking for Q, and there's a relationship between Q and I, and then there's the differential equations. Look for two different things. On a capacitor, if I of 0 is equal to 1.4, determine the charge and current at some time. So we need to identify these things, and then this is where you're really familiar with this already because you've practiced this a bunch of times, and then you know what each of these things are applied to. So we can write the differential equation now, but before we do that, let's identify these different variables. So we're looking for Q of t. Q of t looks like it's going to be the charge. And then I, they give you an initial condition for the I, so we need to somehow relate that with Q since we're looking for Q. So what's I of t equal to? Remember? It's what? dq dt, but what is it in terms of the, what do you call it? It's current, right? Is it current? Current. So the charge and the current, so these are the two things that we're looking for, which means when we solve for Q, we need to somehow find I, and then we need to put these values, this value in for T in both functions. Okay, now we have some other givens here. We're given information about a 200 volt force. So that's going to have to be set to one of the constants. And anybody know what the constant is for the force? Oh, yeah. So the volt measures what? Is measured by volt. What's measured by volt? Energy per charge. So, but what's that constant though? What are we filling in? This is I? Oh. Yeah, what variable does it go to? Well, what we're going to do is we're going to relate it to the, what was the equation again? Let's just write the equation down. Yeah. IR. So that's kind of like what I was looking for. Um, so dq dt plus 1 over c q is equal to v. So these constants I, or the constants r, c, and v have to be filled in with constant that they would give you. So that's what I was hunting for here. And so we got our v figured out. Now we need to figure out what r and c are equal to. So resistance is 1,000 ohms. So 1,000 ohms is going to be a measure of what? Resistance. So that's R or C. And then we have capacitance. So this is going to be C. All right, we're going to put these numbers in so that we can work with them. So we have 1,000 dq dt plus 1 over 5 times 10 to the negative 6 times q is equal to 200. All right, so this is a first order linear differential equation. We can find an integrating factor. We can get rid of this 1,000. So let's get rid of the 1,000 dq dt. So this would be what? 10 to the So we would do an integrating factor. Oh, did we? Oh, I don't know. This is so this is negative 6, and then you're dividing by 10 to the third, right? Yeah. So when you're dividing, you're actually dividing by 10 to the third. That's what you're doing, right? And so you have a positive third, positive 3, negative 6, right? Okay. All right, integrating factor. Now there's something special here when you have a constant. Integrating factor is just the constant times t, e to the constant times t, right? So you can just say integrating factor mu equals e to the integral of a constant we could. So 1 over 5 times 10 to the negative third is actually 200. Okay, so our integrating factor is e to the 200t. Two. Okay. And then we just solve for this, right? We integrate. So it's 0.2 divided by 200. The 2's cancel. It's 1 over 1,000. Always asking. So Q is going to be equal to 1 over 1,000 plus C over sure. Good. Those 8 problems would be a good place to start, and then you can do some modeling. It's due tonight, isn't it? Or you could just wait till 11 o'clock and then do it then. That's what people do. It's only extra credit, so you don't have to do it. All right, we have an initial condition, but our initial condition is given as an I of 0. Oh, I guess, did we finish solving for this? This is Q of T. It's what? Okay, so the charge, is Q the charge or is that I? So as it goes off to infinity, this denominator gets really, really large. So limit as t goes off to infinity of the function q is going to be 1 over 1,000 because this thing goes to 0. So it's just going to be 1 over 1,000. And now we need to figure out what I is equal to be able to solve for the constant. So remember that I was equal to, what is it, dq dt. So this is gone, and we have C. How should we write this? This is like e to the negative 200t. So negative 200 C e to the negative 200t. So that's what I is equal to. And then we can use the initial condition to solve for C. I of 0 is equal to, what is it? I of 0 is 0.4. So negative 200 C e to the 0 power. So C is equal to what? Negative 4.4 divided by 200. 0.4, 4 tenths. 2 divided by I'm blanking. 2 tenths or 2 thousandths? So 4 over 2,000. So that, so 0.002. 0 zeros. All right, so that's your C, and then you put it back into your I and then your Q functions, and then answer the question: what happens in 0.005 seconds? So Q of T is equal to 1 over 1,000 plus 0.002 e to the negative 200t. Oh yeah, it's negative. So put in the value of t is equal to 0.005 seconds, or 0.005, 0.005. And then I is equal to, this is 200 divided by 0.002. That's 0.1. Positive. and then put the value here. So, like in a test situation, this is why you would probably want your calculator so that you can, first of all, be able to deal with numbers like these. And then if I ask for specific values where you have to put in some values in some exponential function, I would be looking for decimal approximations. And so you want to be able to put all that stuff into your calculator. Okay. So there's two main types of these problems. This is an example of the RC circuit, RC series, and then there's another one. What is it? The LR or something like that? Yeah, the LR. And there's one that has all of them, but we're not going to. That's it's a second order differential equation, so we're not going to go over that. So make sure you got a handle on this, and then there's a couple of other mixing or other thing problems, right? A couple of other modeling problems. The mixing and the cooling. I think the cooling problem and the dispersal is almost the same sort of functions. So make sure you got a good handle on that too. And what I mean good handle on that, I mean do like 3 or 4 problems really well and understand it backwards and forwards so that if one of these problems is the problem on the test, then you would know what to do already. And then you would just be using your sheet of notes as like a resource or a guide. I don't want you to use a sheet of notes like like this is the first time you're doing it kind of thing. You need to have gone over this each of these types of problems like 3 or 4 times for you to be able to be successful on the test. Okay. um, so that's a circuits problem. Well, we didn't finish it, right? Just you have one more step here. Q of 0.005 equals whatever that is, and then I 0.005. All right, what else? We done? Can I go? Why would I want to? Uh, if I was going to put the test on Canvas. All right, so I have one from 2014 and one from 2017. 2017? No, I can't do both. Okay, so the last one. Uh, yeah, the one I showed you guys. I did. That was last semester. That was when I used to do practice tests. You want practice tests instead? No. You either get practice tests or you get the actual tests from last semester. Nope. The practice test has the answers, yeah. It also has multiple choice. So you want the practice test or the actual test? Actual test. This is from last semester. Actual? Okay, actual test. All right, we're done. Yay!